In the previous video, we covered everything we need to get started with the confidence interval, so now we're going to go ahead and get started. So here's a reminder of the formula, and also to remind you that this calculation right here is our margin of error. This whole thing is our margin of error. And we covered in the last video how to calculate this value here. So now, a couple things can happen. If we have a smaller sample size n, then the confidence interval itself is going to be wider. We'll say we have maybe 95% confidence that the mean falls between two values, and the values will be much wider apart. So let's take a look at the serial example from the previous video in a couple different ways. So in this example here, instead of 25 observations, 25 cereal boxes, let's look at 16. So we're going to decrease the number of observations. So our n is 16. We're dealing with a 95% confidence interval. So we know for when we have a 95% confidence interval, we know our z-score is 1.96. Sigma is 1.02. Oops, excuse me. Sigma is 0.03, and our x bar is 1.02. So what that means is we'll take our x bar plus or minus, and then our z-score 1.96 times our sigma. So far nothing has changed, but then we're going to square root it, divide and square root by our n value. So when we calculate this, again, remember to calculate your margin of error first. And when we type that into the calculator, our result comes out as 0.015. So if you recall, before we had 0.0112, and now we've got 0.015. So our width actually increased. So the difference between these values, so this was 0.008 to 1.032. And here so this is a difference, a width of 0.024. You can also double that value to find your width. And so if we double this value here, our width is 0.030. So we've got a wider distance between when we lower the number of observations. And that's it written out for you. Now, if we have a larger standard deviation, sigma, then the confidence interval will be wider. So let's think about that. If things vary more greatly, then we're going to have a larger, wider confidence interval. So in this case, we're looking at the same example, but our standard deviation is going to change. So our x bar is still 1.02. We're still dealing with a 95% confidence interval, but this time it's going to be 0.005, and we're still looking at the 25 here. So when we type this into the calculator, we're going to end up getting, let me find that here, plus or minus 0.02. So the width of this is going to be 0.04, and remember that our width over here is 2 times that, 0.024. So this width, 0.04, is a little bit larger. So when we increase our standard deviation, the confidence interval gets wider as well. And lastly here, if the confidence level becomes greater, so instead of 95%, let's say 99%, it's also going to get wider. So if you think about it, if you want to have a greater confidence level, the wider the interval. So if you want to say something with 99% confidence, you may have more variation in what you're saying. Oh, it could be between this smaller and this bigger number. So everything's going to stay the same here, but we're going to do a 99% confidence level. And if we go back to our previous video, we covered the common confidence levels and their z-scores. So 2.576 is the z-score associated with that guy. There we go. So we know that this is going to be 1.02 plus or minus 2.576, and then we've got 0.03 divided by the square root of 25. So when we type that into our calculator, our margin of error changes to 0.015, and that's the same actual margin of error as before, and we know that that width is greater. So go ahead and give these two a try. Press play when you're ready to see the solution. And there you go. So now let's do a couple examples where we're actually determining the confidence levels and the confidence intervals. So IQ tests are designed to yield scores that are approximately normally distributed. A reporter is interested in estimating the average IQ of employees in the firm in California. She gathers the IQ scores from 22 employees, so we've got N equals 22, and records the sample mean as 106, and she assumes the standard deviation is 15. So A says compute a 90 and 99% confidence interval. So the only thing that's going to change here is the z-score value. So let's look at a 90% confidence level. So that z-score associated is 1.645. So we would calculate our interval as the mean, the sample mean, plus or minus the z-score times the standard deviation over the square root of n. So our confidence interval here is going to be 106 plus or minus 5.26. And then for B, we've got a 99% confidence level, so the z-score associated with that is 2.576. And again, if you don't know where I got those, rewatch that previous video. So the only thing that changes is the z-score in this formula. So when we type the margin of error into our calculator, we end up getting 8.24. So these are the confidence intervals. And so use these results to infer if the mean IQ in this firm is significantly different from the national average of 100. So now remember, these are giving our confidence intervals for that national average, that population mean. So let's actually take a look at the 90% confidence level. We're saying that we're 90% confident. With 90% confidence, we can say that the firm is between, the firm mean is between, and I'm going to write it in set notation here. So I'm going to do 106 minus, to get the lower value, 106 minus 5.26. And when I do that, I get 100.74, comma, 106 plus 5.26, and I get 111.26. Now, I can say that with 90% confidence, it differs from the national average because 100 is just below, right? It's 90% confidence that they're in between these values because 100 is outside of the interval. Let's take a look at 99% confident. With 99% confidence, the firm mean is 106 minus 8.24, so that's going to give us 97.76, and plus 8.24, we're going to get 114.24, and 100 does fall in there, so we can say with 99% confidence that the mean IQ in the firm is not significantly different from the national average because 100 falls within that level. And here it is written out. If you want, you can pause it and see it there. For our last example here, we're going to use a table. This data is in your data files. So you can grab it and pull it open into your spreadsheets, Excel, Google Sheets. So I got rid of the portion. These are the weights in grams of 80 hockey pucks. And they want us to do a 90% confidence interval for the population mean weight, assuming that the population standard deviation is 7.5 grams. So we know that we've got 7.5 here. And because it's 90%, we know that our z-score is 1.645. But what we're missing here, so we've got our z-score and we've got our standard deviation. And we can actually figure out n. We could count all those out. They actually tell us it's 80 hockey pucks. So we know that our n is 80 as well. So we need to get this value here. Well, the great thing about Excel or Google Spreadsheets, whatever spreadsheet technology, is you can just go average and then highlight all your values. Let's see, we've got 80 here. So we know there's a bunch. Enter. And it gives us our average. So again, if you double click it, we just did the average for that. And we got 1.66.71. And then we can type this in. You could type it into your calculator. You can also type it into Excel if you want. 1.645 times 7.5 divided by the square root, of 80. and you would get 1.3, let's say 8. And so this is our confidence interval here. We can say that we're 90% confident that the population, the mean of all hockey puck weights, the mean weight of all hockey pucks, and then we'll do that same thing. And we can even go here. So we've got this value. We've got our average, 166 minus 1.38. So 165.33 and 167.1 plus 1.38, 168. This is we're 90% confident that the mean weight of all pucks falls between those two values. And if you want to read it, there you go. And go ahead and give these 3 problems a try. Press pause and then play when you're ready to see the solution. And that concludes section 8.1.